In this lesson, we're going to look a little closer at what makes up matter, what it is that forms the particles that make up atoms, as we start to understand quarks and the Standard Model. So one of the first things we want to understand is how is it that scientists investigate these particles that we cannot see with the naked eye, can't see with any optical instruments? How is it that we even know they exist? How can we do any kind of measurements and quantify anything about these particles? And that's where we'll start. So I like to start with this image on the right here and just maybe you want to pause the video for a moment and just ask yourself, from this photo, and if it's not clear, this is kind of some snow, freshly fallen snow and some tracks in the snow. I like to see what you can infer from these tracks. And if I said just develop a bunch of inferences, a bunch of conclusions, maybe some hypotheses about the organism that made these tracks, what kinds of things would you look at for evidence? What kinds of things would you be confident about? What kinds of things would you maybe need more information about, but maybe suspect? And the reason I like to start with this is because it gets people's brains wrapped around this idea that we can actually find out quite a bit from a picture of the trails of an object or a creature rather than seeing the organism that made it. So, a lot of people will say, well, it looks like whatever made these tracks was traveling in this direction. But hey, maybe people think it's going in this direction. Sometimes people will say it looks like this thing is going at a constant velocity because the tracks are pretty evenly spaced out. Other people might think that the tracks are getting further apart. So they might think that the object is getting faster or the creature is getting faster. Some people might suspect that this creature has more than just 2 feet. Maybe there's 4 imprints at each section, so maybe it's a 4-legged animal. Definitely this thing is changing direction because it's traveling in one direction at one point and it curves in another direction. The point is, we don't have to see what made these tracks to start to make some logical conclusions about the tracks that are made and what creature made it and what characteristics that creature had in terms of speeding up or slowing down or changing directions. Take a look at these tracks. These tracks are made by subatomic particles that are subjected to a magnetic field. And I think we know enough about physics now to start to make some inferences about what particles made these tracks. If you knew the direction of the magnetic field, you can see that some of these particles, if you follow their trails, spiral in one direction, while other ones might spiral in another direction. And that alone is a lot of information for someone with your level of physics to understand that there are particles here that have positive charges. Some objects might have negative charges. You might make inferences about the speed of the particle based on the kinds of circles that they make. The fact that these circles in general spiral towards the middle might make you conclude that these things are slowing down as they are creating these tracks. Again, the point is, and the game that particle physicists play, is try to figure out the nature of a particle by looking not at the particle itself, but the tracks of that particle. One of the ways that we see or visualize particles is by putting particles into something like a cloud chamber, for example. And there's other examples, and you can read about particle physics and how we can visualize or see particles when they are not large enough to be seen with the naked eye. And in this case, what's happening here is we have a sample of uranium-238 right in the middle here. And that sample is decaying, and as it decays, it emits some sort of radioactive decay particles. And the experimenter has placed the radioactive material into a environment that probably has a bunch of pure alcohol dissolved in it, and so it's kind of evaporating in this region. And then the trail of these particles are emitted from this radioactive sample, they begin to make clouds, just like clouds in our atmosphere. So we have this solution of alcohol gas in the air just waiting to form particles waiting to form clouds once a particle is present. And so as these particles travel through here, we can start to see their paths. We don't see the particles themselves, we see the cloud that they produce, but that's enough for us to kind of get a sense of things like how fast are they going? What do they do in magnetic fields? What do they do in electric fields? Are they positive or negative? How massive are they will be kind of indicated by the thickness of the trail. So again, this idea that rather than seeing the particle, we're going to have to do some other experiments that allow us to get a sense of what kind of particles are coming off a radioactive material, because we can't literally see those particles ourselves. So let's just be clear. What have we learned to this point that would allow us to analyze subatomic tracks? Well, we have our hand rules. We can certainly identify if something bends to the left or right in a magnetic field. We can use hand rules to determine the charge on that thing. We know the law of charges, so we know that we should have the same amount of charge at the beginning and end of an experiment, and that might help us to deduce the charges on particles. We know about the forces and the paths of particles in electric fields. They tend to take kind of a trajectory when they are subjected to electric field. We know they accelerate because of electric fields. So we have a lot of math in our back pocket as we go forward to analyze what happens to charged particles in magnetic fields and electric fields. We know the effective voltage to a charged particle in terms of changing the energy of that charged particle. We know what happens to particles in magnetic fields. I mean, the point is, you have, after Physics 30, a whole repertoire, a whole toolbox of ways and math and concepts that allow you to look at a subatomic particle's path and deduce a lot about that particle. So let's take a look at what scientists have done historically to get us to a point now that we understand quite a bit about the subatomic world. Notice this picture on the right, it's worth looking at. It's a picture of Nobel winner Carl Anderson took a photograph. It's a path of a subatomic particle, and that particle, this white streak that's kind of visible right here, was the first time that anybody had ever seen this particle before. This is the first picture of something called a positron. You will know a positron better as a beta positive particle. So it's got two names. I prefer, and you might hear me talk about it as the positron from now on, but this positron, or beta negative particle, this was the first evidence of this particle that had been theorized, but we needed to get some evidence for it in this cloud. This might be a bubble chamber. A bubble chamber is a similar to a cloud chamber, except the particles move through liquid and they leave a trail of bubbles. But this bubble path of these bubbles kind of gave us evidence or proof that there was indeed a particle called a positron. And just if you're interested, this part right here, this white band across here, is a metal plate. So this positron, they actually had it go through a metal plate. And based on this experiment, they could prove that this thing had the same mass of an electron, but a positive charge. So non-electron, positron. Now, as you saw in Carl Anderson's experiment, there's this positron, this thing that is an awful lot like an electron, but has a positive charge. And this is something that quantum theory predicted, that every particle has an antimatter counterpart. So the positron, this beta positive particle, is the antimatter form of an electron, which we see as a beta particle. And so for every form of matter, electron, you have an anti-electron, and the universally accepted way to say an antiparticle is to use the same symbol as the particle, so E for electron, and then put a bar above it. So that's an anti-electron. Where there's a proton, we could also talk about the antiproton. And in terms of characteristics, antiparticles have the identical characteristics, except they have the opposite charge if there is a charge. Neutrons are neutrally charged, so the anti-neutron still is neutral, but as you'll see, it has characteristics that make it an antiparticle other than the fact that it's got a charge. Otherwise, their masses are the same, so 9.11 times 10 to the minus 31 for an electron versus a positron. Everything else is the same, but the charge is different, and it turns out just the form of matter that they are is fundamentally different. Now, one interesting thing about antimatter is that when it collides with its matter counterpart, they are annihilated, and by that, they cease to exist. So this positron meets this electron. If they collide, this annihilation, this destruction, if you want to think of it as of these two particles, produces these two photons. So the mass of both particles is converted into energy. So where is the mass? It's in this form of energy of these gamma photons that are emitted here. Take a look at this simulation, kind of give you an idea. Whenever antimatter-matter pairing meet each other, they annihilate, and the mass is gone and converted into energy, and it's converted into energy to the tune of E equals mc squared, but now we're losing the entire mass. If you think about a nuclear reaction such as an alpha decay, only some of the mass is turned into energy. Even in a fission or fusion reaction, the amount of matter that is turned into energy is a very small fraction of the overall mass. In a antimatter interaction, the entire mass. So if we have this positron-electron interaction, we would convert 2 times 9.11 times 10 to the minus 31 kilograms. 2 because it's both particles that get annihilated, so the proton and the electron. So we would convert all their mass into energy. This would be called, an antimatter explosion if this happened with enough of this material. Fortunately, there is not very much antimatter in our part of the universe. So the opportunity or the number of times that positrons meet electrons is pretty limited. And so it probably does happen as a single event rather than tens of thousands of these things interacting. For anyone thinking about medicine or interested in medical sciences, you may have heard of something called a PET scan. A PET scan is a scan that at its base uses what's called positron emission topography. It takes a positron-electron interaction, and when these two gamma particles are produced, the image can be collected of where that occurred. So the idea would be to inject somebody or have somebody ingest a radioactive isotope that undergoes positron emission. If you put that radioactive isotope and bond it with something like glucose, that sugar will go to select parts of the body. In particular, when they want to take an image of the brain, they bond some sort of positron emitter with glucose. Your brain uses a lot of sugar, so much of that isotope ends up in your brain. And then consider what would happen if you were, for example, doing a math problem with these positrons in your brain. Well, the positrons are connected to the sugar is going to go to the parts of the brain that are most active. And then when the positrons meet an electron, which shouldn't take too long, they emit these gamma particles, and we would be able to then say, oh, there's the part of the brain where there is the most activity. The most gamma rays are coming from this part of the brain because the most sugar was in that part of the brain, and you get the argument. So then we can see what part of the brains are active when certain things are happening. If you're doing a math problem versus reading versus what's the activity of a brain of someone who has had some trauma to their brain, these kinds of things. So as you can see, in order to look at the very small, the very unseen to our eye, we have to start to really take it apart. We have to be able to rip apart atoms to understand what made up atoms. So to find out that there was electrons, the way we did it was we ripped electrons off of the atom. In order to find out that there was protons and neutrons, we had to kind of probe in and smash the atoms up a little bit in order to figure out what they were made of. So a lot of what subatomic physicists do is break things apart and then try to figure out how were they put together in the first place. Now you have to understand, if you want to break things apart, just like in your everyday life, the more energy you have, the more you can break things down into smaller pieces. So consider the energy requirements to begin to investigate the subatomic world. 13.6 electron volts is the ionization energy of hydrogen. If you remember what we talked about with the Bohr model of hydrogen, hydrogen had at its ground state minus 13.6 electron volts. In other words, if we added 13.6 electron volts to that electron, it would be removed from the atom. So to investigate that part of the atom, you need around 10 or 20 electron volts. Rutherford's experiment, you'll remember the alpha particle scattering experiment, involved particles that were being fired, alpha particles being fired at a gold nucleus, and those alpha particles had about 10 mega electron volts of energy. The source of that energy was from a radioactive material. So you want to start looking at electrons, you got to use 10, 20, 30, maybe 100 electron volts. You want to start looking at the nucleus, you have to start getting into your megavolt electron volt range. And then that brings us today. Now we have something in the form of a particle accelerator that can accelerate particles to such high speeds that they have in the order of 3.5 tera electron volts of energy. Then we take those particles that have all that kinetic energy moving along, kinetic energy maybe as much as 3.5 tera electron volts, and then we smash them into a nucleus or something like that and see what breaks free. And then we take our bubble chamber or cloud chamber, put it here, and we can see the particles that come off. And this is really a strange way, but the only way that we can study subatomic particles. It's kind of like the equivalent of taking a piano, dropping it off of a building, and then trying to figure out how it was put together from all the pieces that are on the ground below. So rudimentary, but effective. So where are we at now after all these collision experiments, these smashing piano experiments? Well, we really have what people refer to as a zoo of subatomic particles. And so we have something called the standard model. The standard model, when you hear that, really just refers to, in this case, the particles that make up every other particle in the world. These, what we refer to as fundamental, cannot be broken down yet particles. And there's a limited number. There's not a bajillion. There's a limited number, of which we're only going to look at a limited number of those limited numbers. So we're gonna look at the quark side of the standard model. Here's what's called leptons. So there's different families of particles. You'll recognize some of these, like an electron is a lepton. There's other particles that are related to these things. They have similar characteristics, so they're all considered leptons. Quarks are another thing you may have heard of. And then we have some bosons. So we're going to just dip our foot in the pool of the standard model, look at a couple of things and how quarks make up other particles. But heads up, if you're studying physics at a higher level, you'll start to see more and more of this standard particle, more of this particle zoo. In addition to the standard particles, we have also identified 4 fundamental forces, and you've heard of them all. We can start down here with our studies in physics 20 with gravity. Then we have something called, we haven't studied this one yet, we'll talk about this later possibly. It's called the weak nuclear force. We have an electromagnetic force, and then we have a strong force. So we're familiar with gravity. We've studied we've studied electromagnetic forces, and we've studied the strong nuclear force to some degree. And this chart's a good one. We want to understand a couple things about this chart. I wouldn't worry too much about this section, but the big thing that you want to understand is the relative strengths of this thing, which is kind of surprising when you consider that this gravitational force really is maybe one of the things that you think about every day that permeates your world in your everyday life. It is actually the weakest of all these forces. On this chart, they've ranked the strong force, and they've given it a relative strength of a 1. Well, if the strong force is a 1, look at how weak gravity is, like 10 to the minus 39. So you can only try and wrap your brain around the fact that for as much as you feel like you're being pulled down by gravity, the strong nuclear force that acts between the nucleons, whew, way stronger than that. And then this kind of ranks them, so you can see where they kind of fall. The weak nuclear force is just a little bit stronger, relatively speaking, than gravity. Electromagnetic force is pretty strong in the universe. And you kind of get a sense of that from the constants. Think about Coulomb's constant versus the gravitational constant. This one's like, what, times 10 to the 9 or so, and this one's like 10 to the minus 11 or something like that. So you can kind of get a sense of those things. This column here tells us a little bit about the range, and we've talked about this before. Consider the range of gravity and electromagnetic. They're inverse squared laws, so technically gravity works infinitely far away. So you can take two objects and move them really far apart. Technically, they're still in R, so we can still calculate gravity even though it's very tiny, just like the electromagnetic. These forces, strong and weak nuclear forces, happen within the nucleus, so it's not surprising that they are very short range. And then this column here, no need memorizing anything here, but it is interesting to note that for every force, there's something called a mediating particle, a particle that communicates that force, a particle that lets things know. For example, lets this mass know how hard to pull on this mass, and vice versa. So these are the fundamental forces. The important thing for you at this level is to understand and identify the four, and then know their relative strengths, not necessarily the numbers, but be able to rank them in order of strongest to weakest or weakest to strongest. But we really want to focus our attention on the role of quarks in the standard model. And there's a number of quarks, and they have names, and the names really have everyday meanings like up quark and down quark, and so that might conjure up an image of something to you, but really the reference to up and down doesn't really have anything to do with our up and down, gravitationally up and down. They're just kind of, and in some cases, they're just kind of cute names for these things. They don't really mean anything. The strange quark, for example, is no more or less strange than the charm quark, which I'm sure is charming, but not any more charming than the top quark. Look at the top quark with his top hat. Okay, he's equally charming to the charm quark. At any rate, there's a limited number of quarks, and these quarks make up other particles. And so quark theory would suggest that quarks make up other subatomic particles, but they do not exist independently. Our only evidence of quarks is in these high energy collisions. We can break them apart for brief moments and see evidence of quarks, but they quickly reform, they quickly get back together and form other particles. We're going to focus our attention on two quarks and two anti-quarks. So here's our two quarks over here. And the quarks that we are going to focus on are this little guy here called the up quark, symbolized by this little Dorito-looking thing with its smiley face. And then there's the down quark. And you can see what they've done here is they've said this is an up, so pointing up, this is pointing down, that's the down quark. This would be then their depiction of the anti-down quark. You can see what they've done, made the little black features rather than the white features. And this would be the anti-up quark. So we have our up quark and our anti-up quark, our down quark and our anti-down quark. We're just going to take a little look at how these can be used to to explain, or how we use quarks to model other subatomic particles. I'll just point this out on your data sheet. So we've been working by and large over the years and over this year with electrons, and now we understand a little bit about a positron, and we've got its charge here. We've talked with beta positive and beta negative decay about electron neutrino and electron antineutrino. So we are now going to focus our attention on this little part of your data sheet. And you can see the information here that's provided that quarks have fractional charges. In other words, they don't have a whole charge like an electron has a -1, or a proton might have a +1, or a positron has a +1. An up quark has 2/3 of the elementary charge. The anti-up quark, and this is a feature of all antiparticles, remember, has -2/3 of the elementary charge. The down quark is -1/3, and the anti-down is +1/3. These numbers are really important because they're really a method through which we can make some predictions about what particles will form when we start putting quarks together. So the first thing I want to draw to your attention, and I want you to pay attention to throughout, is the fractional charges on these quarks. You don't have to necessarily memorize them, but you better refer to them whenever we talk about other subatomic particles. So the biggest lesson that I want you to learn about quark composition, or quarks, is we'll use protons and neutrons as our example. If you want to make a prediction about any particle's quark composition, you need to know a couple of things, and there's always rules of the game. So the subatomic particle zoo particles, depending on their groupings, their families, have certain rules applied to them. We'll use protons and neutrons as an example. Protons and neutrons are in the category of family called the hadrons. The first thing you should know about a hadron, and again, don't have to memorize this, you'll see when we're done with protons and neutrons as an example, but I'm just going to show you how you can play particle physics without a whole bunch of information. You need to know a couple of rules. First one is this: if you're a hadron, you always have 3 quarks. So here's a question that you should be able to answer at this point, and it's got really little to do with physics. It's got a lot to do with deductive reasoning. And the question is this: if a proton is a form of matter, and so that tells us it has to be made of matter quarks, it can't be made of antimatter quarks, and it has to be therefore an up or a down or some combination. And a proton is a hadron, so it has to be 3 quarks, and we know the overall charge on a proton is +1. The question is this: what is the quark composition of a proton? All right, so let me just summarize this again. We have to have 3 quarks. 1, 2, 3. Why? It's a hadron. That's just the rule of those things. So we have to put together 3 quarks. So we're wondering what 3 they are. It has to be only up or down quarks, and when we're done, we have to have an overall charge of +1. So if you thought, well, let's just see what would happen if we put 3 up quarks together. Well, the charge on an up quark is +2/3. Imagine if we put 3 things together and each of those things had a charge of 2/3. The total charge of 3 up quarks put together would be 6/3, or 2 times the elementary charge. That doesn't work. So we know that a proton is not up, up, up. It's not 3 ups. So we can rule that out. Now, I hope you have a better strategy than just going through every possible permutation. You could have up, up, down. You could have up, down, up. You could have up, down, down. You could be, well, you could be spending a lot of time with the wrong answers before you get to the right answer. So pause it, take a second. Shouldn't take you longer than about 30 seconds to figure out what is the quark combination for a proton. All right, did you get up, down, up? If you did, I think you're right. And we can just double check it by considering the charge on these things. This guy with his smiley face, positive 2/3. This guy with his smiley face, minus 1/3. And this one, positive 2/3. So when we put those three together, we meet all the conditions necessary for a proton. It's got three quarks. They are all some combination of up or down. And when we put them together, we get a charge of +1, or 1 times the elementary charge. So I think we're safe to say that the quark configuration for a proton is up, up, down. Now, the order that you say these, I know I've drawn it as up, down, up, just because I like the idea of these triangles coming together like this. But as you'll see, and I'm not picky about this, you're just getting into the game of subatomic physics, but there is a pattern, and you'll see it's always, when you talk about protons, we always say up, up, down. We always go U, U, D. You'll see that again and again, because that's just the standard way to do it. And if I have to be honest, I'm not sure why that is. But if you want to summarize for protons, neutrons, antiprotons, and antineutrons, you could probably do this for yourself, but here it is. They're all hadrons, so you'll see they all have three quarks that make them up. The matter particles are always made of matter quarks, so protons and neutrons have nothing but up or down. Antiprotons, antineutrons, no surprise, all anti-ups or anti-downs. And when we're done, each of these quarks, when you consider their charges and add their charges together, the charges of the quarks add up to the charge of the particle. So charge of a proton, we already established this, should be +1, and it is under this configuration. A neutron should have 0 charge. So yeah, take a look at what happens. We have positive 2/3 because of this up. We have negative 1/3 because of this down. We have negative 1/3 because of this down. Overall charge, 0. And once you've done the form of matter, like a proton, the antimatter, you can do the same game with the fractional charges, but take a look. It's the same configuration. If a proton was an up, up, down, then an antiproton, we can cheat a little bit. It's anti-up, anti-up, anti-down. And the antineutron, where a neutron was up, down, down, this is anti-up, anti-down, anti-down. So all forms of matter, antimatter, work this way. Once you know the quark configuration for the matter, then you pretty much, well, you know the antimatter form. It's just the antimatter quarks coming together to form it. So, you know, the hope here is that once you understand, if you're given the rule in terms of the number, if you know the number of quarks that are coming together, if you know the type of quark, and for the protons and neutrons, we said it had to be up or down. We didn't get into the strange and the charm and all that. And you know the overall charge of the particle that you're looking for. I think that's enough, you'll see, to deduce for yourself without any particle accelerators or any prior knowledge. You should be able to deduce for yourself the quark configuration, even if it's something you haven't seen before. So now that we have a little bit of quark theory behind us, I want to revisit this idea of beta decay, because I feel like there might be a couple people with this nagging concern about beta decay, and that is this. If you look at this top example of beta decay, where carbon-14 emits a beta negative particle, or undergoes beta negative decay. So we have this electron and antineutrino coming off, and we have nitrogen-14. Not sure if anyone's like me, but worried or concerned about the fact that I don't know where that electron came from. Like, if we started with 6 protons and 8 neutrons in carbon-14, then I have a little bit of an issue, or I have a concern at least, that instead of having 6 protons, I now have 7 protons. Where did that proton come from? And instead of having 8 neutrons, I now have 7 neutrons. What happened to that neutron, and where the heck did the electron come from? And the answer to that really comes down to quark theory. If you consider beta minus and beta positive decay, both of them have these issues around the number of protons changing, the number of neutrons changing, an electron that seemingly came out of the nucleus but had no business being in the nucleus in the first place. So let's revisit beta decay with our understanding of quark theory, because in quark theory, protons are actually made up of up and down quarks, so are neutrons. So in beta positive or beta negative decay, we have to look a little closer. And what really is happening is, let's use beta negative decay down here. In beta negative decay, the up, down, down quark that we start with as a neutron actually changes. And one of those quarks, one of these down quarks, will actually change into an up quark. So in this case, the neutron now becomes a proton because now it's got an up, up, down. And in that process, it emits a beta particle and an antineutrino. And so it's this breaking apart or this changing of this up, down, down. And this involves the weak force. And it's the weak force that is actually occurring between these quarks. And the change in this down to an up involves a force particle, the weak force particle, as well as these other particles. But in the end, what we need to understand and wrap our brains around is that neutron is actually changing into a proton, emitting a beta particle. And by doing this, we obey all the laws of physics. You'll notice that we still have the same particles around. We have the same conservation of charge. And if we involve quark theory, we can explain this phenomenon where, let's go back to it, where we seem to be kind of gaining particles and losing particles, but in fact, everything's pretty good. Everything still works out just right. Not sure why I can't write here, but it's not that these 6 protons, we magically got a proton. We traded a neutron, which went down in number, for a proton. So the neutron turned into a proton, and in the process emitted this electron and antineutrino. And a similar thing happens down here, except in this case, a proton turns into a neutron, emitting a neutrino and a positron. So beta decay can be better understood if we start looking at quark theory. So a lot of stuff going on in here. This is really a series of things. They all tie together. This idea of investigating the subatomic world, understanding of subatomic particles and fundamental forces, and a little bit of a closer look at the fundamental forces and particles when we look at quark theory and how quarks come together to form protons and neutrons. So I encourage you to go back, treat this presentation really in the 4 parts that go with the 4 sections of your chapter. Chapter goes into a lot of detail, so I would not recommend trying to commit a lot of that to memory, but you can definitely get some clarification if you look through the book and get a better understanding of some of the things, or a different explanation of some of the things that I've presented here for you today.